So today my topic is elastic and inelastic scattering using ab initio nuclear structure on quantum computers. And so my name is Weijie Du, as Dr. Berry has introduced. So I will quickly jump to the main body of this talk. The outline of this talk is the following. First of all, I will introduce the basics. Can you see my cursor actually?
Yes.
Good,
yes.
good.
Yeah.
So the first part is going to be the basics of quantum computing, and the second part is going to be the time dependent basis function on qubits. This is the algorithm we are developing, and the third part is in the third part, I'm going to introduce our future efforts, and also I'm going to do a summary of on this talk. So this talk is mainly going to be about the application of quantum computation techniques in nuclear physics. Sorry. So there's a grand challenge in nuclear physics, that is to describe the nuclear structure and dynamics of the nuclear matter at all scales based on the most fundamental degree of freedom. And however, this is a very difficult question to address. For example, we expect to see exponential growth in the number of states as the particle number increases in the target system. So overall, one word to say is that to address the nuclear many-body problems in a classical way is very, very difficult. And yeah, and this is a model problem for you to introduce, for you to interpret the exponential scaling here. This is a scaling problem for classical computation. The question is, what is the dimension of the wave function of a spin system? So to address such a problem, we need to introduce the Hilbert space, and the Hilbert space has a dimension listed as follows. First of all, if you have one particle in this system, you would need a dimension 2 Hilbert space for spin up and spin down. Then for for two particle system, you will have dimension 4 to power 2, and for three particle system, you will need 8 basis 8-dimension Hilbert space, and for n particle system, you will need a Hilbert space of dimension 2 power n. And for the laptop, nowadays laptop, the memory is typically 1 terabytes. Therefore, we can store the information or the wave function of a 40 particle system. However, to store the even larger system, to store a 100 particle system is beyond the capability of the largest supercomputer nowadays. Not to say to operate such information. And people might think if it's applicable for supercomputing techniques to eventually address such questions. It's not so promising from a nowadays perspective. The problems are the following. First of all, exascale supercomputers is going to be extremely power consuming, and as the size or the computation power grows, the supercomputer will require complex architecture and also the algorithms. And also the chips, the transistor size on the chip is decreasing. However, there must be a limit there. Nowadays, it's going to be the transistor size is going to be 3 to 10 nanometer. But if we keep shrinking that transistor size, quantum effects will eventually manifest. So, since it's very hard to expect that classical computer will eventually succeed in solving nuclear many-body problems, and we have to find another way to address such nuclear many-body problems. Here comes a similar idea raised by Dr. Feynman. He said that let's make the computation fully quantum mechanical. Since the nature isn't classical, so if you want to make a simulation of nature, you'd better make it quantum mechanical. Now, Dr. Feynman suggests to do everything in quantum mechanical way. Therefore, some clever minds in the beginning of this century, I mean, might be later, might be 30 years from now, sorry, I would like to say some clever minds at the start to introduce the concepts of quantum computation at the very end of the last century. To go from the classical to quantum mechanical computation, here are some comparison between classical computer and the quantum mechanical computer. Quantum computer. In a classical computer, people used to use a classical bit that is a definite, that can be represented by two states. First is a 0 state, the other is 1 state. And that corresponds to the transistor on and off on a chip. However, to do for a quantum computer, the elementary unit for a quantum computer is a quantum bit, so-called qubit. The information carried by a qubit is a wave function or state vector of the qubit. It is given by the superposition of this 0 and 1s. Note that the alpha and beta stands for the complex numbers, and the state vector here carried by the quantum bit can locate at anywhere around this Bloch sphere. That means for a quantum bit, it carries infinite number of the states until the measurement collapse this wave function and the outcome become manifest. And the quantum computer makes use of the quantum principle to do calculations. Here are the quantum principles that quantum computers makes use. First of all is a superposition principle, and second of all is entanglement. And making use of these two principles makes a lot difference. In principle, there are fundamental changes in computation methodology and algorithm design, and also since the information becomes quantum mechanical, the information storage and manipulation also sees a significant change. And this slide shows you how quantum computer operates on a qubit. I'm showing a NOT gate. Here I'm showing an elementary operation of the quantum computer, so-called NOT gate. The story is the following: the quantum computer operates an X gate on the initial state to get the final state. And for this, and graphically, we can see on this graph that if we put the x-axis as a 0 state and y-axis as a 1 state, what this gate does is to flip the initial state from the one side to the other side to get the final state. And this operation has a matrix interpretation. If we build if we find the matrix representation of this operator in the basis of 0 and 1, this would be the matrix that corresponds to this operator. And we can see that's the initial wave function, which is alpha and beta in the representation of formed by the basis of 0 and 1. This is the wave function, and if we operate the operator on this wave function to get the amplitudes flipped. And there are also various other operations, such as the phase gate, the Hartmark gates, the gate, etc. Now, quantum computers make use of the quantum systems to perform calculations. Such quantum systems need to be under well control and sufficiently isolated from the environment. And quantum computers can potentially circumvent the roadblock of exponential cost in computing science. Also, quantum computer offers a natural way of processing quantum information. Classically, to express a quantum state of n-particle system, it will be intractable as n increases, since the scaling is exponential. However, quantum computer offers a better way to do that. In principle, people would need a polynomial n qubits to store the quantum state. And in essence, as I see that, the quantum computers provide a natural way to express and manipulate quantum states, and it also offers promising opportunities for treating nuclear many-body problems. And due to the rapid development of the quantum computation technologies, a lot of innovations and discoveries are made in quantum algorithm. However, this is also a fast evolving field, and nuclear physics and this development benefits nuclear physics to a very large amount. Greatly. And here are the interesting problem set that shall see this benefit. First of all, it's going to be many particle problems, and the system is, and second of all, the system is strongly coupled system. And third of all, it's about the real-time evolution and dynamics of the nuclear system. And here are a detailed list of the potential applications of quantum computing. First of all, people can do a quantum field theories and fundamental symmetries investigation from a different perspective. And second of all, people can also work on real-time dynamics. That includes our topic here today, which is a nuclear reaction. And third of all, people can also study dense matter, such as neutron star and heavy nuclei. Now, the application, as I said, the application of quantum computing techniques in nuclear physics is a newborn area. There are a lot of very interesting papers that is already done or published in this field. Some of them are about quantum field theory, some of them are about the neutrino nuclear scattering, and also some of them are about the investigation of atomic structure, nuclear structure, and also we would also see some real-time dynamics of lattice gauge theories, and so on and so forth. I will only take a few of the topics from the literature. Oops. And now I'm going to introduce some elements of the quantum computing. That's about the first of all, I will introduce about the concept of the qubit system. Now, quantum computer, the building block of quantum computer is the quantum bit, which in short is a qubit. It is a basic element in the quantum computation, and it is usually made up by, it is usually a two-level quantum system. For example, a spin half system, where spin up stands for the 0 state, and spin down stands for the for the 1 state. Here are some here for the one qubit case. That the 1 qubit case, that the qubit will carry for the 1 qubit case, the wave function is a general superposition of the basis state. This is the wave function carried by 1 qubit, and it is a superposition of the basis states 0 and 1, and the normalization is necessary to make this wave function, to make the probability of the wave function to be 1. And for the 2 qubit case, it is the so-called register, which is made up by a bunch of qubits. The register, the wave function of the register is made up by 4 states, and for each basis states, they are the direct product of the single qubit basis, so-called 0 and 1. For example, for the 0, 0 state for 2 qubit case, we have a 0 direct product with 0 to give 1, 0, 0, 0, and for and so on and so forth. Also, for the wave function of the 2 qubit case, normalization is equal. The wave function is normalized to 1. And we will have also for an arbitrary n qubit case, it is just the superposition of the basis state. And again, it requires 2 n basis states, and each of them are constructed based on the single qubit basis by direct product. And also the wave function of the n qubit system is normalized to 1. And from here, I'm going to introduce the other concept of quantum gates. Quantum gates is controlled local. Quantum gates are controlled local unitary operations applied on qubits. For an identity operator, for an identity gate, it does nothing to the qubit. Therefore, it is equal to the identity operator. In the representation formed by 0 and 1, we will have the identity matrix as follows. And we will also have the X gate, which corresponds to the NOT gate in the classical computation. It will just flip the state of it will just flip the basis. For example, it will flip 0 state to 1 state, and it will also flip the 1 state to 0 state. And in a matrix representation, the matrix of the NOT gate is as follows. Also, we will have the Hartmark gate, which generates the entanglement. And in the matrix representation, it has the following interpretation. And we have also the phase gate, and this gate is a bit interesting. What it does is as follows. If this gate sees a 0 state, it does nothing. It does nothing. However, once this phase gate sees the 1 basis, this 1 basis will acquire an extra phase given by this phase gate. And in the matrix representation, this has the matrix of this R phi. The phase gate looks as follows. And there are also some two qubit gates. For example, here we have the CNOT gate. For the CNOT gate, this is controlling the upper line stands for the controlling bit. The lower line stands for the target bit. And what this gate does is that if you input a 0 state here in the controlling gate, the target gate sees no change. That means if you input the 0 state as from here we will determine the first bit, the rightmost bit, to be the controlling bit, and the leftmost bit to be the controlling bit, and the rightmost bit to be the target gate, target bit. So if this is 0, the controlling bit is 0, there's no change in the target bit. Therefore, 0, 0 maps to 0, 0, and 0, 1 maps to 0, 1. However, in the other case, if this controlling bit is in the 1 state, then the gate will there will be an X gate, poly X gate acts on the target gate. What it does is to flip the 0 and 1 states. For example, if initially the target gate is 0, then after the application of the X gate, it will be flipped to a 1 base to 1, and vice versa. In the matrix representation, the CNOT gate looks like this, and there are also some control phase gate here. Also, this is a controlling bit. The bottom line stands for the target gate, and for this bit, so for the leftmost bit, it stands for the controlling bit, and the rightmost bit stands for the target bit. Again, if the controlling bit is 0, no operation is acting on the target gate. Therefore, 0, 0 maps to 0, 0, 0, 1 maps to 0, 1. However, if this controlling bit is in the 1 state, 1 vector, then the phase gate R phi will act on the target gate. However, this R phi will give the second target bit a phase only when the target bit is in the 1 state. Therefore, you will see 1, 1, 0 maps to 1, 0, and 1, 1 maps to 1, 1 with the phase. In the matrix representation, the controlled phase gate looks like this. There are also swap gates that swap swap the state of the 2 qubits. For example, 0, 1 is swapped to 1, 0, and 1, 0 is swapped to 0, 1. And for more information, I listed this link in this page for your reference. And the other concept of quantum computing is a quantum circuit. For this talk, I'm going to focus on the quantum. I'm going to focus on the circuit language of the quantum computation. Therefore, here I'm going to introduce the quantum circuit. So quantum circuit is a sequence of quantum gates that output the solution to a certain problem. And here is an example of a very simple quantum circuit. And for the quantum algorithm, it is to design a quantum circuit for a particular problem, and the performance of the quantum algorithm is characterized by the number of gates and the runtime as a function of the problem size, which is a scaling of the problem. And this shows you a very interesting problem where quantum supremacy is expected. Here, it is about quantum Fourier transformation. In essence, it does the quantum computation of it is a quantum version of the fast Fourier transformation. And for the quantum Fourier transformation, for the elements of the two power n, two fast Fourier transform 2n number of the elements. Quantum Fourier transformation requires little n square gates. However, for classical fast Fourier transformation, that would require n times 2 power n gates. Therefore, you will see a exponential speed up via the quantum computation. And in the second part is about the time-dependent basis function on qubits. This is the algorithm we are developing. The motivation for this algorithm is as follows. First of all, we want to construct a unified ab initio theory for nuclear structure and the reaction. Second, we want to study complex nuclear processes, especially those for rare isotopes, because of the short lifetimes of the rare isotopes during reaction. A bunch of reaction processes will happen, and it is very important to track every reaction branch during the real nuclear processes. And also, we want to investigate nuclear interactions for both on and off shell properties of the nuclear system. And this theory is very important for the fast growing field of rare isotope beam facilities around the world. For IMP, here, the scientists here are building a new facilities in Huizhou, Guangdong province, which is a place I'm here now. It is also about doing rare isotope experiment. It is also about doing rare isotope experiments, and we will see a large amount of requests for series with predictive power for nuclear structure and the reaction. And the background of this investigation is as follows. There are existing methods such as no-core shell model with continuum, and there are also no-core shell model with resonant green method, and gamma shell model, harmonic oscillator representation of the scattering equation, and Green's function approaches, and also the nuclear lattice effective field series. However, these successful methods fail to retain the full quantum coherence during the calculation, and they are not quite as powerful to track all potentially possible nuclear processes during the reaction. And if we want to scale the reaction problem up, we need large and complex. If we want to study large and complex reaction systems, more and more resources are going to be required. And as I discussed before, this is as the particle number of the reaction system grows, there is an exponential scaling up for the computational resources for a classical computer. That's why we come to the following solutions. First of all, if we want to retain the full quantum coherence, and if we want to track all the potential possible nuclear processes, we can do the calculation with information on the amplitude level, and also we can do real evolution for the reaction processes, for the reaction system, and to address the exponential scaling of the computational resources, we can rely on the quantum computation techniques. So the time-dependent basis function on qubit algorithm has the following properties. First of all, it is a unified structure and reaction theory. Second, it is based on successful quantum structure theory. And third, it is an ab initio method. Fourth, it is a non-perturbative and time propagation method, and it retains full quantum coherence and entanglement during the calculation. And it circumvents the exponential cost in computational resource in simulating real quantum many-body dynamics. To illustrate this method, we go with a demonstration problem. It is about the Coulomb excitation of deuterium system by peripheral scattering with heavy ion. This is a setup for this model problem. Here we rest the target system, which is a deuteron entrap at the origin, i.e., that is, we put the central mass of the deuteron at the origin, and we apply a heavy ion to fly from negative L to positive L naught, with the impact parameter B. And during the flight of the heavy ion, the target, which is deuteron, will see a time-varying Coulomb field, and this time-varying Coulomb field will excite the system, excite the deuteron system, and this is a time-dependent Hamiltonian of this scattering system, where this H naught stands for the free Hamiltonian or the reference Hamiltonian of the target. It is made up by the kinetic energy, the interaction of the neutron and proton, and also the trap we apply here to target to make this problem easier to make this problem clearer as a demonstration problem. And this VINT, V interaction, is a time-dependent part. It can be calculated by the interaction between the time-varying Coulomb field and the charge density distribution of the target. And here I'm going to introduce some elements of the TBFQ algorithm, time-dependent basis function on qubits algorithm. First of all, we are going to construct the basis representation for the ab initio nuclear structure from the ab initio nuclear structure calculation. We are going to divide the whole system. We are going to divide the Hamiltonian of a system into two parts. The first part is the free Hamiltonian, and the second part is a time-dependent external interaction. And with the free Hamiltonian, we solve the basis. We solve with the free Hamiltonian. We solve the eigenfunction of this target system, and this beta b, beta j are the eigenfunction of this deuteron system, and this EJ are the corresponding eigenenergy. And with these eigenfunctions or eigenbases, we can construct the basis representation to solve the time evolution problem. And here is a game plan for the TBFQ. First of all, we would like to prepare the initial state, and it can be entangled state. And second of all, in step 2, we are going to time evolve the state with a totalized evolution time evolution operator. And third of all, we are going to do measurement after the time evolution. This is the overall algorithm of this. This is the overall algorithm. With the initial state, with the initial state for the target, we for the reaction system, we time evolve this initial state to get the final state. And this is the explicit expression for the time evolution operator, which is made up by the integration of the Hamiltonian of the reaction system, where this H naught is a Hamiltonian for the free or the reference for the free Hamiltonian of the deuteron system, and this V interaction is the external interaction caused by the interaction caused by the Coulomb time-dependent Coulomb field. And to solve this time evolution operator, we first discretize the reaction time, and we divide the system into a bunch of different time step. And in doing so, this integration can be divided into a sum of terms, each scaled by the difference time. And next, we can do some further approximation of this time evolution operator by the totalization scheme. Basically, it turns the experiment. Sorry, basically we would obtain the sorry. After the totalization scheme, we would have the approximation of the time evolution operator as follows. Since we are doing the first order totalization, the error of this approximation is to the order of difference times square. And next, we are going to qubitize the basis set. Since we are working with the basis representation constructed from the eigenbasis of the reaction system, in the qubitization processes, we are going to map each of the bases to a specific qubit configuration here. And this mapping procedure, it takes log n, the log of the number of the basis dimension. The next question is to address is to turn the time evolution operator into a quantum circuit. Here's the details of what we are doing with this model problem. First of all, after we solve this, after we solve the free Hamiltonian, we retain 7 basis states of the target solved via the ab initio nuclear structure calculation, which is the triplet S naught, triplet D1 multiplets, and triplet P naught state, and triplet P1 multiplets. And for simplicity, we also prepare the initial state to be this state, which is anti-parallel to the axis. And in the dynamical processes, we keep only the E1 radiative transitions in the dynamics. That is the dynamics enrolled in the time evolution, included in the time evolution operator. And then during the qubitization processes, we map the qubits. We map the basis states into different configurations of the qubit. Into different qubit configurations. And here we map the first state to 1 0 0 0 0, second to 1 0 0, and so on and so forth. Note that for this model problem, we would require 3 qubits and we will put the missing one, that is 111 state, as a trivial state here. And to design the quantum circuit, we further make two approximations for the interaction term. That is, we assume the interaction in the Hamiltonian to be made up by a sum of terms here, which is V1 plus V2s, and so on and so forth up to Vn. And for each of such term, we assume that this term can be split into a time-dependent part and a time-independent part. Note that this time-dependent part comes from the external part. It is, for example, in this problem, it comes from the time-varying external field. And this part, Wi, stands for the intrinsic part for the deuteron. This part is time-independent, and it denotes the intrinsic, it determines the intrinsic properties of the nuclear system under reaction. And the next, and if we do the above approximations, the time evolution operator for one arbitrary Trotter step in the basis representation sees the following decomposition. That first, for example, for this term stands for the contribution of V1 in the time evolution operator, and this term stands for the contribution of V2 in the time of evolution operator, and this part stands for the contribution of Vm to the time evolution operator. Note that here's an example of the time evolution operator in the basis representation with a case of m equal to 2. What we have here is that this unitary, if this unitary turns into the quantum circuit, the following form is what it should be. Note that this U1 and U2 and UH0, 1, 2, 3, 4, 5, these 5 gates are time independent. They are fixed for all the Trotter steps. And these two are the diagonal, these two stands for the diagonal unitaries here. And they are time dependent. However, the circuits correspond to the circuits corresponding to these two time-dependent unitaries can be designed to be directly parameterized by the scattering time. Therefore, overall, the quantum circuit for each Trotter step can be designed to be directly parameterized by the scattering time. And the complete time evolution operator in the basis representation is made up by a sequence of such Trotter step, such time evolution of Trotter steps, and the circuit can be designed accordingly. Note that with the scheme I have introduced above, each module here is simply parameterized by the scattering time, and the overall circuit is a sequence of such modules. And we do the calculation on Qiskit. It is a virtual. We did on a virtual quantum machine, and we do not run. We have run the quantum calculation on a real quantum computer. But since the current circuit design is not optimal, therefore a bunch of noise come up and ruins the numerical experiment. However, finally we shifted to the virtual quantum machine, which is simulated by the by Qiskit. And we see that on these graphs, we see that the red line stands for the theoretical calculation by classical computers, which is in the work we have done and published years before. And the blue dot stands for the quantum simulation based on our quantum algorithm. And we see a good agreement between the classical and quantum results for all the states we kept in this model problem. And this panel H and panel I, stands for the calculation of the observables. We also see very good agreement between quantum calculation and the classical calculations. Finally, I will go to the discussion of future efforts and the summary. This method, this algorithm can be generalized to be to real scatterings, where the channels and the states are increasing dramatically. And this scheme can also be generalized to study real dynamics in gauge fields. For example, the electron scattering in intense E&M fields. For example, the laser facilities going to be here in Huizhou. And also, we can also study the quark scattering in color field. And we can also do particle production and evolution in Glasma field. Here is a summary. Since I suspect I'm running a bit out of time, I will leave the summary here. And thank you for your time.
Thanks, Weijie. Actually, you ended up exactly on 45 minutes from the time you started to speak. Very, very nice presentation. Let's get a quick look here at your summary. And okay, so that
in this talk, quantum computing techniques employ quantum mechanical principles to outperform classical computers. The rapid development of quantum computing techniques shed light on many challenging problems in nuclear physics. And we developed the TBFQ algorithm to simulate low energy nuclear scattering on quantum computers. And this work can be further generalized to various scopes of research areas in nuclear physics. And we're still improving this algorithm, so stay tuned.
Great, great. I think one point that it was implicit in what you said, but maybe people who read the originally posted version of the paper on the archive didn't catch the significant difference from what you're saying now. Could you elaborate on that? In the originally posted version on the archive, there was a hybrid quantum classical computing algorithm presented, and yet today I think you're doing everything fully on the quantum computer, correct?
That's right. That's right. We go with some assumptions, and finally we find this decomposition scheme here, which stands for that. For example, I'll elaborate on this term, which stands for the contribution from a V1 in the external interaction. Sorry, the contribution of V1 in the external interaction to the time evolution operator, which is UV1TK, where TK stands for a specific trotter step, trotter time. What we do is the following: we would apply a transformation matrix U1 and U1 dagger to transform from the basis representation to the eigenrepresentation of this Wi. This transformation is, since this Wi is assumed to determine the intrinsic properties of the nuclear system on the scattering, therefore it's time independent. The time dependence of this external interaction comes only from the external field, time varying field. Therefore, this U1 and U1 dagger is explicitly time independent. What is time dependent is the diagonal stuff, which encodes the information of this AIT coming from the external field explicitly. Therefore, after this, after such decomposition, we can design the quantum circuit once for all with only the parameter tunable according to the scattering time here.
And in the problem, in the application you demonstrated here, little m is, how many actual terms are there in this expansion? Little m.
I mean, in general, it can be. I mean, in general, it depends. It depends on the leading terms in the interactions. For example, the ENM, multiple decomposition, and in the real calculation, we did 3.
3, yeah. So I think the important thing I would comment is that, well, this looks like an approximation, but it is actually not an approximation in the model problem that you're addressing. It's actually a feature of this particular scattering problem that was recognized, identified, and then taken advantage of. But my feeling is it's actually a general feature of a lot of scattering problems where a small number of time-independent terms with perhaps complex scattering amplitudes, AI of t in your case, can represent very, very complicated, nonlinear, non-perturbative scattering problems similar to what you've done. So it increases the depth of the calculation that you have to do, but without increasing the complexity of this, the number of qubits that you need. This was, I think, a particularly interesting aspect. The number of qubits is fixed by your original eigenbasis representation for the solution of the H0, which is the nuclear structure, in this case, the nuclear structure problem originally.
Yes, yes.
And I'm particularly interested in pointing this out because we have in the audience, we have people who are working to solve the other part of this problem, you might call, that you don't address, which is how to solve for the eigenbasis in the first place on quantum computers. Our Tufts University colleagues attending have been working on that part, which is not something you address. You assume that that's a solved problem and go forward from there because you use all the states of the system that you choose to include in the scattering dynamics as your basis representation. So,
yes.
So yes. I see your work as complementary to the work that was mentioned last week, in our previous seminar by Peter Love, which featured the Tufts University projects, the projects led by Tufts University.
I see.
Yeah. Anyway, I'd like to open it up for other questions and comments from the audience.
I have a question. Hi, Weijie. This is Will Kirby from Tufts University.
Good morning.
Thank you for the talk. I wonder if you could comment on how the number of gates required for this method will scale as you increase, say, the number of particles, like if you want to go to more realistic or larger scattering problems like you mentioned.
Yeah, this is a very difficult question currently to me. But what I know is the following. So we are applying some standard method to do the decomposition of this U1 of these transformation matrices, and the so-called method. The method has a name of the method is called the column by column decomposition scheme. It scales with almost the exponential number of gates, and we are so far looking forward to improve such decomposition methods to get fewer or more efficient quantum circuit for each transformation matrix. Yeah.
Can I offer an additional comment? So actually, the way this problem is set up, if you could go to the diagram, Weijie, that shows the transitions, this problem is actually not dependent on the number of particles in principle. It actually depends on the number of eigenstates of the target system that you want to include. So he has 7 states included and therefore 3 qubits. So if you were only going to include 7 states of a 500 particle system, it would still be a 3 qubit problem. What in the real world, what changes is that as you increase the number of particles, probably the number of physically interesting states that you can populate will also increase. And that depends more on your scattering energy and what is the actual nature of your probe. Is it electromagnetic or is it a strong interaction probe? And that's a very different scaling behavior than normally we think of for many body problems. So in a way, the particle number dependence has been factored out by requiring you to use eigenstates of the n-body problem as input or approximations thereof. Okay, so that's it's not explicitly dependent on the number of particles, but on the number of eigenstates you think are physically interesting in the scattering problem.
Yeah,
sorry.
Another feature of this algorithm that we are working with the basis representation. Therefore, what matters is the basis we employed from the target system, and this the number of qubits scales as a log of the number of the bases. In this case, we can possibly, this is one of the benefits of this algorithm. Yeah.
This is really interesting. Thank you for the detailed answer. I want to ask a slightly provocative question, and so I apologize. If maybe I'm misunderstanding, but if the size of the basis is fixed, where do you see quantum advantage coming from? Like an advantage over a classical computer? Or I must have misunderstood. Yeah. Go ahead. Sorry.
Sorry, it's very late night here. Can you repeat your question?
I might have misunderstood something that James said. But if the size of the basis is fixed, then where does the advantage over a classical computer come from? Am I wrong that the size of the basis is fixed?
I would say that I would do the following comparison. If we are working, if we let free the design of the quantum circuit, let's forget about this part we are currently working on. So we are currently working on, and let's working on the basis dimension explicitly. If we are working with a classical computer, we would need n. The dimension of the problem is going to be n, right?
Mm-hmm.
If we are working with the quantum computer, then according to this mapping procedure, this qubitization procedure, we would have a log2 reduction in the problem dimension.